Hello, everyone. We have already 30 attendees, and we are about to start. So my name is Jaime Martin, the CEO of eProsima, and I'm going to be presenting DDS and the use in robotics in this FIWARE webinar. So the agenda for today is going to be, first of all, I'm going to talk a little bit about eProsima FIWARE, and later I'm going to introduce DDS, what is DDS, the architecture, a very quick demo, and what is new in the latest release of DDS for ROS 2. Because in this presentation, we are going to center the robotics part in ROS, the robot operating system that is the de facto standard in robotics frameworks. And half of the presentation is going to be conducted by Francesca, and the team leader of XRCE-DDS and micro-ROS, that is ROS for microcontrollers. So let's start with a very quick presentation about our company, eProsima. We are a small company focused on middleware, especially on DDS. We are members of the ONG, the organization that standardized the DDS standard. DDS stands for Data Distribution Service, and is a standard of a publication subscription middleware for critical systems. We are members of the Technical Steering Committee of ROS 2. ROS 2 is the latest version of the robot operating system, and we are key contributors of ROS. You are going to see in this presentation. We are also contributors of ROS Industrial, and we are FIWARE members and the representatives of the FIWARE Robotics chapter. So our products are mainly fast DDS, that is a DDS implementation, pure open source implementation that is adopted by ROS 2 and also is a FIWARE enabler. Our second product is Micro XRCE-DDS, that stands for DDS for Extreme Resource Constrained Environments, basically microcontrollers, and it's the base of micro-ROS, and it's also a FIWARE enabler. And we have a third product that is an integration service with other protocols, such as the FIWARE Context Broker, that is the central component of the FIWARE framework. And this product is the base of the ROS integration service, also called a SOS, System of System Synthesizer, and is going to be a future FIWARE enabler. So let's talk about Fast DDS. As I said here, formerly Fast DDS. We changed the name in the latest month because initially we implemented just the protocol, not the DDS API, the DDS standard API, but now we implement the full DDS standard API. This middleware is powering ROS 2, that is the latest release of ROS. So why a new middleware? Because you have out there thousands, literally, of options for middleware. Well, you have a middleware for every use case, I would say. When you need real-time requirements, that is, for example, the latency measured in microseconds, more than in milliseconds, or high throughput requirements. In this case, you take advantage of the publish subscribe architecture, because in the publish subscribe architecture, the publisher sends the data directly to the subscriber without intermediate brokers. So this is a lot faster in terms of throughput and latency. When you have low bandwidth requirements, for example, you have Wi-Fi or radio networks, when you have many-to-many communications, decoupled architecture, and you need different quality of services for different data links, and also when you need efficient data models, because in DDS the middleware knows about the data model. The data is not opaque like in other middlewares, and you can make use of the data structure to increase the performance and have POSs depending on the contents of the sample you are sending. We will see later more about this. In the case of fast DDS, it's a pure C++ implementation of DDS. We implement the DDS API and also the underlying protocol, the DDS interoperability wire protocol that is called RTPS, the real-time publish subscribe protocol. We implement the full DDS security implementation, so fast DDS is very secure. We have also remote procedure calls and very good documentation. A lot of platforms are supported: Windows, Linux, Android, macOS, iOS, but also real-time platforms like QNX, VxForce, and real-time Linux. But well, we are going to talk later about microcontrollers. In the case of microcontrollers, we support specific operating systems for microcontrollers. For example, NAT, Xephyr, and FreeRTOS. And there are many ports developed by the community because FastDDS is very open. It's, we don't use many third-party components, and you just need POSIX compliance, Berkeley sockets, and you can port FastDDS to whatever the system, the platform. It's adopted by ROS and comes with an Apache 2 license that is a very open source license. So why did they select FastDDS for ROS 2? First of all, because it's open source and free, and all features are open source. That means that we have no premium version of FastDDS. Everything is open source, and our model is an open source, and business model is an open source model, which asks just for support and services. We have a big community, and our roadmap is totally aligned with the ROS 2 roadmap. Also, we are members of the technical steering committee of ROS 2. There are like 12 companies, including companies as important as Microsoft, LG, Open Robotics, and other super big companies, and our company. Because our components, our products are used as the base of ROS 2. FastDDS is the default middleware for ROS 2. The DDS security is the base of the secure ROS 2. Our Micro XRCE-DDS is the base of micro-ROS, and we are the coordinators of the micro-ROS project. And our eProsima integration service is the base of the ROS 2 integration tools. So DDS is a middleware that allows you to connect anything. But basically, in this case, we are talking about sensors and actuators. You can consider a robot as a set of sensors and actuators. And you can think in a distributed robot. It's not only the typical wired robot with sensors and actuators, but imagine that you have also IoT components in a room and the robot. You can consider the whole set a distributed robot. DDS is really a family of specifications. It's a specification of an API, but also the specification for the wiring interoperable protocol, and specifications for dynamic types, security, remote procedure calls, mappings to different languages, web-enabled DDS, XRCE-DDS, a lot of different specifications. And you have a lot of implementations out there. You have about 10 implementations, 10 important implementations, and well, with so many implementations, you have many languages supported: C, C++, Java, .NET, and many platforms. You have in the architecture here your application on top. Then you have the DDS layer. That basically the DDS is a library you can link to your application, and behind this library there is the transport, and the transport could be whatever: UDP, TCP, share memory, serial, whatever you need. So DDS is historically adopted by defense and aerospace. It has a very long history of success in this kind of critical applications, and for example, is adopted by the European Air Traffic Control for air traffic control interoperability, and many defense organizations in the US and Europe, for example. We have here in Europe, Spain, UK, and well, in the US, basically all the important organizations, including the US Army, for all kinds of applications, mainly command and control system. And in the case of robotics and automotive, well, you have ROS adopted DDS, FIWARE also adopted DDS as their interface to robotics. Many drone companies and Drone Code, that is the main OS platform for drones. AutoSAR, that is a consortium of the most important automotive companies, and well, projects of autonomous driving like AutoWare, Apollo, Baidu, and a lot more. And well, we have really, in the case of Fast DDS, a lot of different customers and partners. We're going to see just oops, a little bit the number of customers we have, a lot of them. And we have around 30,000 clones per month of our repo. So really thousands of users that for middleware of this kind is really a lot. So let's talk a little bit about the architecture of DDS, how it works. In DDS, you have to imagine that you have a global data space. And in this global data space, you define topics of information you want to publish to or subscribe from. A topic is basically a name and the structure of the topic. Imagine, for example, the position of a vehicle. You have an ID and the X and the Y for the position. And in this global data space, the participants, the applications, join the global data space and create publishers and subscribers. And you just start the discovery of the different nodes, the different participants happens automatically. You don't need to set up anything, and you just start publishing or start subscribing. It's really easy. That is one of the main advantages of the DDS standard. And it's really fast because there are no brokers out there. Directly the publisher sends the information to the subscribers. So why DDS? Well, DDS is a totally decoupled model. There is no single point of failure. And it's decoupled in many dimensions. For example, in the space or location dimension, because the discovery is automatic. Basically, the different participants send broadcast messages to announce the presence, and everything happens magically. And you have no need to set up anything. When you have an application, a working application, and you change your network topology, everything is going to be working again without any problems. Redundancy. It is possible to configure redundant publishers and redundant subscribers in primary, secondary, or takeover schemas. And this is really, really very easy. In the case of DDS, it's just one line of code. And usually in the typical client-server architectures or other middlewares, this is usually a nightmare to set up. It's decoupled time in the sense that when you join the global data space, you just start publishing, and you can set up DDS to store the history of the samples you published in order to send the history out to the late joiners if you want. And also in the case of the subscriber, you don't have to pull the publisher. You just declare your interest in subscribe to a topic, and as soon the publishers have data for you, you're going to get an event in your subscriber telling you that you have new data. It's also decoupling in the terms of a platform. That is typically many middlewares. You can have a participant in Linux, another in VxWorks, another in Windows, and everything is going to work properly. And also, it's decoupled even in implementation, because the DDS wire protocol. You have you can have fast DDS, for example, in one side, and RTI DDS in another side of the communications, and everything is going to work. You have really a lot of different quality of service policy. For example, you have policies for the resistance to set the history, for the joiners to establish, in the case of lifespan, expiration date for the data samples. You can set up resource limits to limit the amount of resources you are going to consume in your applications. You can set up the reliability of the protocol. You can say if your protocol is going to be just preserved for or reliable, and if it's going to be reliable, how it's going to be the reliability protocol. How are you going to send the heartbeats, the ACKs, the NACKs? You can set up different partitions for your system, or you can set up easily with ownership and ownership strength the redundancy of your publishers. So in order to, well, we will take a lot of time to discuss all of these QoSs. So what we are going to do is we are going to show you a very quick demo, showing just a couple of them, as you can download this demo from our website, and it comes with a user manual, and you can play with the demo and understand what are the available QoSs you can use for your application. In this demo, that we call sales demo, you have 3 different topics: square, the circle, and the triangle. And the structure we are sending is very simple. the color, the position, and the size of the shape. So let's do the demo. Quickly. For example, here I have, I'm going to publish on a square, right, in this case, and I'm going to subscribe here to this publication. So with our configuration, the discovery happened. Also, I can publish here another one, let's say a blue square, and you can see that the subscriber that is in the center of the screen is getting both. And I can do even more. I can publish, for example, a yellow square. And here we can see all three together. So what we are seeing here is that I didn't set up anything. You can download this application and run the application in your network, and everything is going to work. Okay. So let's do another quick demo. For example, I'm going to publish here a red square with redundancy, that is exclusive ownership, and a strength of 100. This is going to be the primary. And here I'm going to publish the same square. That is going to be secondary, in this case with an strength of 50. And here I'm going to subscribe. And you can see that what you are getting in the center of the screen is just the primary subscription. But if I delete the primary, or it hangs for whatever the reason, immediately the subscriber is going to get the secondary publication. So very simple and very fast to set up. So well, for Francesca demo, Francesca is another room of this office, and I'm going to publish here an orange square, and she will complete the demo with micro-ROS. So let's continue with the presentation. So fast DDS is selected by many organizations. In this case, we are talking about robotics. We are talking about ROS, the Robot Operating System. Why is this? Well, first of all, because we have many interesting features in the latest release. We are releasing our real-time behavior, that is no dynamic memory allocations. You can set up a fast DDS to allocate all the memory at startup, and this is very important for real-time applications, because dynamic memory allocations are usually not very predictable. We don't use blocking calls, and you have available both synchronous and asynchronous publishing in terms of that. Well, you can use your own thread in your application or a middleware thread to publish the data. We have also intra-process communication. We are the only implementation out there with this feature open source. And we implemented a discovery server. I'm going to talk about that later, but this is very interesting for Lucy environments. So in the case of the discovery server, to the left, in the left you have the typical discovery mechanism, that is the automatic discovery, and it's based on multicast. Initially, all the nodes announce their present saying hello, I am here, but there are many situations in which you cannot use multicast. And as a matter of fact, multicast doesn't work very well on Wi-Fi and enterprise Wi-Fi environments. In those cases, you can set up a discovery server, and the nodes are going to register themselves in the discovery server. That can be redundant. You can have one or many discovery servers. And during the discovery phase, they are going to use the discovery server to discover the other nodes, and afterwards are going to talk to each other directly. So we are super complete for a open source implementation. So here we are comparing the other two open source DDS implementation supported in ROS2, and you can see that we support many features like security, micro-ROS support, dynamic types, real-time behavior, server-based in discovery, it's cell memory transport, and the possibility to use internet in fast DDS, and the other implementations out there doesn't support this kind of features. So, well, we have a team that is totally devoted to robotics, and by the way, we are hiring. So now microcontrollers. Francesca is going to take the lead and is going to present XRCE-DDS and micro-ROS. So Francesca, please.
Hello. Okay, yes, so I will be leading the second part of the presentation, which will be focused, as Jaime was mentioning, on microcontrollers. So let me share my screen. I might also be taking off the webcam, but I wanted to make a connection in this. Okay. Yes, can you see my screen? Okay, I guess everyone is muted, so I hope that, yes.
Yes.
Tell me if anything is going wrong, but okay, thanks.
Yes.
All 40 persons. No, it's enough, thanks. Okay, thank you so much. Yes, I will also unshare my camera. And okay, so the specific software or product that I'm going to talk about are these Micro XRCE-DDS and micro-ROS. We will be going through them in detail. And they are sort of the alter egos of FastDDS and ROS2 for the embedded world. Okay, so first of all, let me get started by introducing a little bit the product themselves and myself. Okay, so Micro XRCE-DDS is an open source library which was fully developed and maintained by eProsima here. And it is the first implementation of the DDS XRC protocol, which was defined by the Object Management Group, OGM, which is the same that created and maintained also the DDS protocol itself. In turn, micro-ROS is also, well, open source, but it was developed as part of a bigger project, especially a UE funded project that is called OFRA, by a partnership of members that includes some companies, well, eProsima to start with, the FIWARE Foundation that is hosting this webinar, and also some other big companies such as Bosch and PIAP. And eProsima significantly, is the coordinator of this European project. I am Francesca Finocchiaro, and I'm currently leading the team that is involved with developing this micro-ROS project within eProsima, and as such, also the coordinator of the OFRA project. Okay, so let me give you a brief overview of what we are going to discuss. So first of all, I want to give a little bit of an introduction of about embedded systems and why they need a whole new paradigm for entering the robotics world. So why not using directly DDS and ROS2? And so what limitations of these two protocols they overcome. Then I'm going to present the first software here, that is Micro XRCE-DDS and related to DDS. I will explain the logics underneath, that is that of the DDS XRC protocol, and then address our implementation of the standard, with an emphasis, with a special emphasis on its most important components that as we will see, are the client and the agent. And I will explain how they behave and interact. Finally, I will present a small demonstration that, as was mentioning Jaime, it's a demonstration of how this Micro XRCE-DDS is integrated into the DDS world. And to do so, I will directly interact with the same shapes demo application that Jaime was presenting, that is moving shapes around, okay? And I will perform a live demonstration of that. After this, I'm going to address micro-ROS. First of all, I will discuss its relationship with Micro XRCE-DDS, then describe its architecture and specifically compare it with the architecture of ROS2. And then I will list all the hardware that are supported by this project up to date. Okay, and finally, I will also present an application that we have developed here at eProsima to showcase its functionalities and stuff, but it won't be live. It's a use case that we already developed, and I will a little bit explain it, okay? Okay, so to get started, let us speak a little bit of the systems addressed by these two protocols. So we have just seen the wonders, so to say, of DDS as a distributed communication protocol based on a data-centric publisher-subscriber model, and also of ROS2 as the ideal API library to build robotic applications that uses DDS as a middleware. However, as Jaime was mentioning, a robot is most of the time to be intended as a set of integrated IoT devices, each in charge of a specific electronic or mechanical component that cooperate to generate a holistic robotic application, where they all build up to carry out one or more robotic tasks. And these IoT technologies most often are constrained to embedded systems, and as such, they have real-time requirements. And because of this, the market is demanding more and more communication protocols and robotic applications that can fit into this low resources or embedded system. So first of all, what characterizes such systems? An embedded system usually will be played by a microcontroller that is basically just a microprocessor that has an integrated memory and peripheral interfaces. Because of this, it has usually real-time computing constraints, and will be a more basic and much simpler system than the standard microprocessor. And because of this, it has constrained resources, namely the memory, both in terms of storage capacity and of RAM, and also a microcontroller will have a limited power and speed in processing, so an overall limited processing performance. So what are the benefits of bringing DDS and ROS to these systems that have constrained resources? So basically, the main aspect can be seen is that the software functionalities in an embedded system are much closer to the hardware, meaning that they can be more directly interfaced with sensors and actuators that, of course, are critical in the IoT and robotic usages. Also, if we think of industrial scale production, the advantage is pretty clear, since these kind of systems allow to cut down substantially production costs, resulting in a potentially faster and seamless automation of lots of processes. And so why do we need to change the paradigm of the protocols that Jaime just exposed? This is basically due to the fact that both DDS and ROS2 are very heavy libraries, mostly programmed in languages such as C++, sorry, that are unfit for these resource-constrained devices that I was just describing, such as microcontrollers. So the market somehow was in need of lighter software that anyhow need to be compatible with DDS and ROS2 in order to ultimately benefit from all the full-scale advantages of these products. So in this presentation, we will see how these protocols combine these key features. So be lighter in the first place, but also be easily integrated in the DDS and ROS world. Okay, the idea basically is isolating a simpler part of the library that takes care of the microcontroller side from a more complex entity that runs instead on a more powerful machine and is in charge, this entity, of bridging the low resource device with the fully deployed DDS and ROS worlds. Okay, the solutions have also the advantage that they are designed to work on different platforms and with a variety of operating systems, and we will see this also. Okay, so let's get started after this very long introduction with describing the Micro XRCE-DDS. Okay, so this is based on the DDS XRC protocol, which is a wire protocol, and it is in charge of implementing the communication between the two fundamental components of this protocol, which are the client and the agent. Okay, so this is the first of the main three features of the protocol, that is of having a client-server architecture. So this seems to imply a change of paradigm with respect to the publisher-subscriber paradigm that we have seen that characterizes DDS. But really, this is just a part of the story, since, as we will see, this architecture is basically a bridge that allows the microcontroller world to access the full data-centric model, publisher-subscriber-based, offered by DDS. How so? So in this client-server scheme, the clients are the entities that run into low-resource devices. Then the DDS XRC protocol is in charge of passing the requests and messages to another entity, which is the agent, that is hosted by a more powerful device. And also the wire protocol sends the agent's responses back to the clients, okay? This means, this architecture means that the protocol follows a request-response pattern, okay? Now, what does the agent do? The agent is able to then communicate with the DDS global data space by means of another wire protocol, which is, well, it's called the real-time publisher-subscriber protocol, and it is the one that the proper DDS builds upon. Okay, so in this DDS world, fully deployed, the role of the agent is that of forwarding the requests of the client to the global data space by creating a client proxy that is able to interact with DDS by means of all the standard entities of a DDS domain, such as the participant and publisher, subscriber, topics, all the nice features that we have just seen in the Jaime presentation. Okay, so this proxy really acts as a proper application using DDS as a middleware, and therefore is able to convert the client into a first-line player in the DDS world. Okay, the architecture, this is the final key features that I want to mention, is that the architecture is connection-oriented, meaning that a handshake needs to happen between these two actors, so the client and the agent, for the communication to take place, and then the agent creates a sort of an avatar that acts on behalf of the client and crucially keeps track of the status of the client during the whole process, even, for instance, if the client gets disconnected. Okay, so this is the basics of this protocol. So let me give an overview now of our implementation, which is the first implementation. So Micro XRCE-DDS is the first implementation of this DDS XRC protocol, and is composed of some libraries, but the main libraries are the client and the agent. There are also other libraries, crucially a generator tool and a serialization library, but here we won't get in such a depth as to discuss them in detail. Okay, so we will just focus on the client and the agent. So the communication between these two entities happens over a transport layer that is pluggable, meaning that it is agnostic about the transport that is used. By default, as we can see in this diagram here on the right, Micro XRCE-DDS provides UDP, TCP, and serial. Okay, and there is also the possibility for the user to define its own custom transport. Okay, over these transports, both best effort and reliable communications can be implemented depending on the type of messages that are meant to be exchanged. The protocol is interoperable between operating systems. And this is, well, thanks to the fact that the operating system dependencies are treated as pluggable modules. So the user basically can easily implement his platform modules to the eProsima Micro XRCE-DDS client library in its own platform. By default, the project can run over Linux, Windows, and 3 more real-time operating systems that we will discuss more in detail here. Okay, so in this slide, I want to discuss the operating systems that are supported by Micro XRCE-DDS, but also by micro-ROS, as we will see later on. Basically, the two main entities of our library, what operating system they do support. So the agent has a very heavy library, and for the moment being just runs on standard operating systems such as Linux and Windows, even though we are right now working to port it to other operating systems. On the other side, the client, which is a much lighter library, apart from running on Linux and Windows, also runs on real-time operating systems. But okay, so what are these real-time operating systems then? So we have said that the client runs into resource-constrained systems, and that in general, an embedded system controls physical operations of the machine that is embedded within. So it often has real-time computing constraints. So basically, real-time operating systems are operating systems that are specifically intended to serve real-time applications that usually will have time-critical usages, and therefore need to process the data as it comes in without buffer delays. So to address these needs, real-time operating systems rely on an advanced algorithm for scheduling tasks. which has well-defined time constraints. So our client, the Micro XRCE client, there are many such RTOSs, and our client crucially supports the 3 RTOSs shown here that are NATEX, Zephyr, and FreeRTOS. All them on top of this scheduler expose POSIX compliant interface. Okay, so let's go on with the client library. So this is a light library that is programmed in the C99, and it consumes really few resources since it is dynamic memory free completely and fully relies on static memory. Okay, it follows a profile concept that enables to choose to add or to remove some features in configuration time. And this allows basically customizing its very size, so the size of the library, allowing it to make it lighter, even lighter if some features are not used. Okay, as part of these profiles, the user can choose between several transport layers, as we discussed before, so by default UDP, TCP, or serial, and the communication with the agent will be carried out by the chosen transport. The communication of the client is performed by streams or communication channels, and 2 types are allowed, the best effort and reliable. Okay, the client, what it does is sending requests to the agent to create entities on its behalf that are then mapped to proxy entities in the DDS world by the fast DDS middleware. Okay, so this is one part of the story, the client. Now we see the agent. Okay, the agent, we have seen that is a heavier library as it is in charge to communicate with the full deployed DDS. So it is programmed in C++11. And it is connected to the DDS global data space by another wire protocol that is the one supported by DDS, and it is the RTPS, the real-time publish subscribe. So the agent crucially here is acting as an intermediate player, allowing the client to communicate with the DDS network as any other proper DDS actor could do. So publishing and subscribing to data topics in the global data space. So this is why before I was saying that even though this protocol relies on a client-server architecture, ultimately it allows benefiting from the full publish-subscribe architecture of DDS, because the client ultimately is acting as a full DDS player thanks to the agent. Okay, and the agent does so by creating a client proxy that basically acts on behalf of the client with full DDS functionalities. Agents keep track of the client status, even if the client gets disconnected. And again, of course, it supports the same transport protocols as the client. And also it supports the best effort and reliable streams. And then the agent basically is in charge also of reporting back to the client. That means forwarding back to the client all the things that have been happening in the DDS world and where the client proxy is acting. Okay, let's now focus a little bit on how the communication between the client and the agent takes place. This slide really helps visualizing, okay, how this communication goes on, how it flows, okay? So we can see that, as we have said already, it follows a request-response pattern. It starts by an explicit handshake between the client and the agent. Notice that the client might either know the IP and port of the agent from scratch, or it can acknowledge the existence of agents on the network by means of a discovery mechanism. that allows basically discovering agents by UDP. The reachable agent will then respond to this discovery call by sending information about them, such as their IP and their port. And this can happen either by multicast or unicast. So once they have shaken hands, the client will start sending requests to the agent. The first thing that the client does is creating a session for which the agent will respond by informing how this operation went. So if the session was created or what. Okay, and this step is basically is the one in charge of generating this client proxy that I have been talking about just now in the DDS world. Okay, so after the session and therefore the proxy has been created, the client keeps sending requests to the agent, such as creating entities in the DDS world, or publishing or subscribing, so anything that one can do in the DDS world, okay? And the agent will each time respond back, either by providing information of the request outcome, and also, as I've said before, by forwarding information coming from the DDS world directly to the client. Okay, so this basically is gives an idea of the conceptual model, and now it's time to do the demonstration. This that we were mentioning before. Okay, so here we have the board that we will use for this demonstration of the capabilities of Micro XRCE-DDS. This is a board, an ST board, which is running FIWARE natively, and it's also an interesting board because it has a lot of sensors integrated in it. A humidity sensor, temperature sensor, but most of all, the one that we are interested in, that is this one that I'm pointing at. Okay, I was covering it, and basically this is a time of flight sensor that is able to measure the distance of an object placed in front of it. So here you have the microchip, and this microchip, well, the microcontroller is running a Micro XRC client, and specifically a publisher application. Okay, here in the computer, what we have is a shell where we will be running an agent of Micro XRCE-DDS, and here we have another shell from which we will start an application which is called Shapes Demo, and it's basically an application which is uses FastDDS as a middleware, which is based on FastDDS. So let's see how this application looks like. Okay, so this application basically is this one, and we will see that it's called Shapes Demo because depending on the topic received, or well, it depends on whether you can publish or subscribe with it, as with any other DDS application. You can subscribe or publish to topics that are basically geometrical shapes of different sizes, colors, and position in this basically white space. So we have said that here we have a client who will be publishing the measurements received from this sensor, distance sensor. Okay, so here what we do is basically we run an agent in this shell. Okay, here you see the agent running, and the agent is in charge of sending the measurements of the sensor to the DDS. Okay, here this is not receiving anything yet because we have not created the entity that is fundamental for this communication, which is a subscriber. I am creating a subscriber, and now you see very I'm sorry, okay, and now we see basically that green square has appeared, whose position along the y-axis is changing continuously as I am moving my hand in front of this time of flight sensor. Okay, and basically this is proving the communication between our Micro XRC client, which is compiled and running in this board, and fast DDS, which is at the base of this application by means of the presence of this agent. Again, so okay, this is the presentation. I hope that it convinced you of the wonders of Micro XRCE-DDS. And that was all for the moment. Well, that was all regarding Micro XRCE-DDS. And let's now move to the second part of this of the talk. It will be faster, I promise. I'm sorry, because we are running a little bit out of time, which regards micro-ROS. So what is micro-ROS? To understand that, let us draw an analogy with the DDS-ROS2 relation, okay, that can help us understanding what micro-ROS is with respect to Micro XRCE-DDS and with respect to ROS2. So ROS2 is a robot operating system which is composed of a set of high-level libraries that are organized in layers, whose middleware interface is constituted by DDS, and specifically ROS2 in this moment uses as a default middleware eProsima fast DDS implementation of the standard. In the same way, basically, micro-ROS can be considered as an adaptation of those same layers to low-resource systems and to their needs, having as a middleware interface the Micro XRCE-DDS protocol that we just explained, okay? So let's discuss a little bit in detail of this. Micro-ROS, in a nutshell, we could say that basically puts ROS2 onto microcontrollers. Indeed, traditionally, ROS in general has stopped at the microcontroller boundary, even though robots, as we have seen, contain many of them. And usually they have been integrated through serial protocols. However, on the one side, this is error-prone, and also many existing sensors and actuators have proprietary firmware that cannot be changed, because manufacturers are usually worried that user changes might break them. Therefore, this is why the micro-ROS project has been focusing on bringing full microcontroller support to the ROS2 ecosystem. Okay. We have seen already that one of the benefits of having a ROS node running near to the hardware level is that all the hardware peripherals are available. And so that your micro-ROS node can directly interact with low-level buses such as SPI or I2C to interface with sensors and actuators. Okay, so the main features of micro-ROS are full layer compatibility with the ROS2 architecture, which we will see in the next slide. Also, the possibility of creating a ROS node with full ROS2 functionalities, such as publish, subscribe, service call, timers, executors. All of these are present in micro-ROS. Also, as we have seen, the middleware transports are fully customizable. Then, once again, it follows a client-agent logics in a one-to-one mapping with the same entities of the Micro XRCE-DDS. And also, it can run on several real-time operating systems and on several microcontrollers. And to do that, crucially, it offers a versatile build system that allows selective cross-compilation depending on the software and the hardware that the user needs. Okay, so here, as promised, there is a full layer-to-layer comparison between ROS2 and micro-ROS, okay? That will be useful to those of you who are familiar with ROS2 already. Okay, so the architecture has been designed to be analog, okay? On top of everything, of course, run the applications that are interfaced with the outmost layer of both systems. In the case of ROS2, these layers are three, of which the most commonly used are the C++ API, which is the RC LCPP, and a Python API, which is the RCLPy. Okay. However, C++ and Python are not fully supported in every embedded platform. Okay. So basically, in order to be compliant with most of the embedded platform and real-time operating systems, micro-ROS only partly uses the RCLCPP API of ROS2, but also provides a C user API, which is called the RCLC. And also, it is directly interfaced with the lowest, with lower lying API, which is another C API, which is present both in micro-ROS and ROS2, which is the ROS client library, the RCL. Okay, so sometimes an application will have to be directly interfaced with this layer. Okay, this layer in turn lies just on top of the RMW, which is the ROS middleware interface. As already discussed, its implementation, okay, in the case of ROS2, this is an implementation of DDS, and specifically the default one used by ROS2 at the moment is fast DDS by eProsima, while in the case of micro-ROS, the only basically existing middleware is the Micro XRCE-DDS client. Okay. In turn, of course, the middleware runs on the operating system, which is either Linux or Windows in the case of ROS, which are apt to run on powerful microprocessors, while it can be either one of those in the case of micro-ROS, but also, as we have seen already, micro-ROS will run on top of an RTOS, a real-time operating system, and the supported ones are Zephyr, NATEX, and FreeRTOS. Okay. Of course, well, ROS will run on a powerful system with a microprocessor, and micro-ROS is designed to run on microcontrollers. Okay. At the very moment, micro-ROS is supporting dashing, but we are working on and almost there to port it to Foxy, which has been released by ROS2 last week or something more. Okay. Okay, so we already discussed of the software supported by micro-ROS. We now want to discuss a little bit about the hardware. So what kind of platforms are targeted by this kind of protocol? Micro-ROS specifically targets mid-range microcontrollers. Okay, what are these? Okay, currently what we support are some STM32 microcontrollers, such as those that are mentioned here. I won't go through them. I mean, you can read them explicitly, and the board that supports such microcontrollers, and specifically the board that support micro-ROS, are shown here on the right. Okay, so what are the characteristics of this kind of devices? So typically they will have about 1 mega of flash memory, 200 kilobytes of RAM memory, and consumption of less than 500 milliampere. Okay, so this is what really we were discussing before, so what low resources means. Okay, there are of course microcontrollers that have even more constrained resources, so that's why I am saying that we target mid-range microcontrollers. Okay, so they also have a general purpose input-output pins, and oops, sorry. Okay, and as communication peripherals, many USB, Ethernet, SPI, WART, I2C, and so on. Okay. So the boards that we support that are shown on the right, as I was saying, are the Olimex LTD STM32 E407. Well, okay, yes, I won't go. So an Olimex board. These are the default supported by micro-ROS, a Crazy Fly drone, and an STM32L4 Discovery Kit IoT, which is crucially the one that I used before for performing my Micro XRCE-DDS demo. Okay, and micro-ROS has several use cases that were implemented here at eProsima and also by our partners in the offer project that showcase all the functionalities that can be achieved on systems of this kind run by these microcontrollers with micro-ROS. Okay, one of them I want to show here in this presentation, just one of them. And this was implemented in our team during the quarantine, so that's why it's in a house and with the spices. But I mean, it's really indicative anyways. Okay, what it represents, it is a robotic arm that is grabbing some objects, some spices, boxes, by basically sizing their position by means of micro-ROS. Okay, and this has potential applications in a lot of fields where automation of processes is needed, and specifically it could have an application in the sector of automated warehouses. Okay, this gives only part of a much larger video that you can find here at this link. And what it shows is a ROS2-enabled robotic arm, which is connected with a time-of-flight sensor, which is located at the base of the arm. Okay, the sensor, once again, as the sensor that we have shown before, is able to measure the distance between a target object and the base of the arm. Okay, it is operated by an Olimex board on which the operating system that runs as an operating system Zephyr. Okay. Then a micro-ROS application, client application, runs on Zephyr and is in charge of passing the distance measurements of the sensor to the software that is controlling the arm kinematics. Okay, the software in turn runs into a Raspberry 4 that is also hosting the micro-ROS agent, which is in serial communication with the client and is acting as an intermediate actor that passes the messages received from the client to the ARM packages, which are ROS enabled, as I was saying before, and are in the Raspberry. Okay, the ARM is then instructed to grab the object with the millimetric position, depending on the distance that the sensor has communicated to micro-ROS, and well, will relocate it to a different position. This is just one of the many use cases that we have developed here at eProsima, and I hope it's able to give you an idea of the functionalities of micro-ROS. Thank you for your attention, and sorry for being so long in my presentation.